So actually, not so that's a good question. I'm actually not going to be here Friday or Monday, but I do plan, I was going to probably sometime tomorrow, make a video covering the material that like for the next couple sections to post for you guys to watch. So that's the plan. Yeah, so I'll also post that on Canvas. We will not meet Friday or Monday.
So if I only got to, but like the only time that day was like Friday.
Sure. That's totally fine. You do not have to come in person. It's totally okay to watch the video after the fact. So today let's talk about vectors. So let's say we want to plot the vector v equal to 2i plus 4j plus 3k. Pretty standard notation. When you're talking about I, j, and k, you're just talking about how much in the x, y, and z directions. If I was plotting this vector in the three-dimensional coordinate system, I would really just kind of be plotting the point 2, 4, 3 to start off with. So I'm going to go 2 in the x direction and 4 in the y direction and 3 in the z direction. And then try to find that point. So I'm going to do the usual thing where I go over this much and that much, and then over like that, down like that, and then up 3. Welcome. So here is the point 2, 4, 3. Here, I'm about to draw, is the vector v 2i plus 4j plus 3k. A couple things about this vector. Well, a couple things about notation. So this is pretty standard notation, but there's probably like 3 standard notations at least. Another way you could write this is v equal to bracket like that, 2, 4, 3. People also use regular brackets like square brackets as well. It would be totally acceptable to write it as 2, 4, 3, or even a vertical. These are all totally fine ways of writing vectors. Sometimes people even use parentheses, which I find particularly annoying because we also use that notation for points. So I will probably not ever use that notation, but sometimes people do. So what is a vector exactly? It's a length and a direction, or a magnitude and a direction. So this vector v, the magnitude of v, is just how long it is. So it's going to equal, we usually use a double kind of absolute value notation for magnitude. Sometimes people use a single, like single absolute values also is totally fine. But this is kind of the more standard way of writing it. And the magnitude, we're just going to calculate by calculating the distance from the origin to where it ends. So it's really just the square root of each component squared and added together. It's going to be 2 squared plus 4 squared plus 3 squared, which is going to be square root of, excuse me, 4 plus 16 is 20 plus 3 is 29. So the square root of 29. Magnitude is just the length, is another word for length. Direction, on the other hand, is a little bit more interesting. So the magnitude is the square root of 29. The direction of the vector, well, sometimes you might start off by thinking like you could describe the direction as some angle measurement from some axis, but that's really kind of complicated. Really, when we talk about direction, we just want to talk about what direction we are pointing in. I'm using the word to define the word, which is terrible. So I personally would say that this vector is in the direction of 2i plus 4j plus 3k. But the problem with that is that you might give a different answer that is equally valid. You might say, well, James, multiply everything by 2, you're still pointing in the same direction. Or multiply everything by 32, you're still pointing in the same direction. If someone asks for the direction, we'd really like everyone to give the same answer. So when we talk about a direction vector, we usually talk about a vector of length 1. So the direction of v is really going to be the vector v divided by its own magnitude. So this new vector will have a length of 1. Let's see. If I do this, I've got the vector 2i plus 4j plus 3k divided by the magnitude, which is the square root of 29. And I'm just going to divide each component by that. So I'm really going to get 2 over root 29i plus 4 over root 29j plus 3 over root 29k. I'll point out that when you talk about the direction of a vector, you're still talking about a vector. So this vector has magnitude root 29 and direction 2 over root 29i plus 4 over root 29j plus 3 over root 29k, which is kind of a mouthful, but that's what it is. I will point out or note that this has a magnitude of 1. And that is usually what someone means if they say, give me the direction of this vector. I mean, tell me the unit vector that is in the same direction as the vector we started with. This process of dividing by a vector's magnitude is called either unitizing it or normalizing it, is usually a better word. And then often you will hear people say that a vector is just a length times a direction. So we often like to think about expressing the vector v as its magnitude times its direction. Well, all you're going to do is take the magnitude, which is the square root of 29, and multiply it by 2 over root 29i plus 4 over root 29j plus 3 over root 29k, which seems a little bit unnecessary, but it's worth remembering because later on you're probably gonna have some homework problems where like you have to do like there's just some weird kind of stuff, and remembering that a vector is really just that vector's magnitude times that vector's direction can help you kind of reset what you're thinking about and figure out where we're going. A couple other language things here. Vectors have a magnitude, or if you prefer length, and direction. A good example of this would be velocity or force. Whoops, you can't see anything I'm writing. Sorry about that. On the other hand, scalars are just magnitude or have just magnitude. An example of this would be something like speed. So we talk about how fast something's going, that's just the magnitude of, like, if you talk about how fast you're driving a car, well, I'm driving at 70 miles per hour, but if I want to know kind of the direction I'm driving, that's more informative, and that's more something like a vector.
What is a scalar?
A scalar is the real number. For example, literally any number on the real number line, whether positive or negative, is a scalar. Whereas a vector is not a scalar, right? It has a direction and a length. Yeah. So the nice thing about vectors is a lot of how they work is pretty straightforward. For example, adding and subtracting vectors is really not hard. It works kind of how you hope it would work. For example, if we have, say, the vector u equal to 3i plus 2j minus 4k, and the vector v equal to I plus 5j minus 7k. Well, if you want to add those vectors together, u plus v, we just add the like components together. So you're going to get 3i plus I, which is 4i. You're going to get 2i plus 5j, which is 7j. And you're going to get negative 4k plus negative 7k, which is minus 11k. Subtracting also works the way you hope it would, meaning u minus v is going to be 3i minus I, which is 2i, 2j minus 5j, which is minus 3j, and negative 4k minus negative 7k, which is plus 3k. But that's not very informative as far as what's happening geometrically. Let's look at an example that's easier to draw in 2 dimensions. Let's say we have new vectors. Let's call them a. Yeah. Right. So not exactly, but you're on the right track. So what I should say is I, J, and K are unit vectors in the directions X, Y, and Z. So I is really the vector 1, 0, 0. And J is really the vector 0, 1, 0. And K, sometimes people write arrows over them. I usually don't, but I happen to be doing it here, is the vector 0, 0, 1. So really, when I write the vector 3i plus 2j minus 4k, what I really mean is 3 times 1, 0, 0 plus 2 times 0, 1, 0 plus negative 4 times 0, 0, 1, which gives me the vector 3, 2, negative 4. Okay, I was going to say, let's look at an example that's a little bit more easy to draw so you can see what's happening when you add vectors, really. Let's say we have A being the vector 3i plus j, and B is the vector I plus 5j. Or if you like, just to kind of remind ourselves of notation, you could write A as 3, 1, and B could be 1, 5. So also perfectly ways right. When you add them, what we do is we kind of add them head to tail. So if I'm going to graph the vector 3i plus j, I'm just going to go over 3 and up 1. So here's the vector A. Starts at the origin, ends at the point 3, 1. And then the vector B goes over 1 and up 5. So it starts at the origin and goes over 1 and up 5. Vectors don't have to start at the origin. We just like to draw them that way because it's easy. Literally, you can put this vector anywhere else and it's still the same vector. Meaning, I can actually put B over here as well. I can go from the end of A over 1 and up 5. But I can also do the same thing from the end of B. I can add on A and go over 3 and up 1. And so this resulting vector starts at the origin and ends at where A and B added together end. That vector right there is A plus B. And notably, it's exactly over 4 and up 6. So A plus B, really just doing 3i plus j plus I plus 5j, which is giving us 4i plus 6j. So adding vectors is super easy. You just add the like components together. Graphically, what's happening is you're drawing the vectors head to tail. So you draw the first vector, and then you put the tail of the next vector on the head of the first vector and draw it. You start at the tail of the first one, and you end at the head of the last one. Adding vectors, not too terrible. Subtracting graphically, I will admit, I always have to remind myself of how it works. So if we're going to subtract these vectors, let's see what happens. So let's say I want to do A minus B. I'm still going to start off by drawing A and B. So yeah, same thing. 1, 2, 3, 4. So here's A again, over 3 and up 1. Here's B again, over 1 and up 5. If I want to do A minus B, what I'm actually going to do is I'm going to draw negative B and then add A and B together. So to draw the negative of a vector, you literally just turn it in the opposite direction. So if that's B right there, here's negative B going left 1 and down 5. There's negative b. And if I want to do a plus negative b, I'm just going to tack on negative b onto the end of a. So here's a minus b. See if I can draw this well. I want to go over 1 and down 5. Yeah, right, over 1 and down 5. So I'm just gonna make sure my picture looks good. Or if you like, you could go minus b plus a. Order of addition doesn't matter when you're adding things, typically. There are some other things later on where order of addition or actually order of multiplication actually matters. But here, vectors doesn't matter which way you order, add them, totally fine. So here, starting at a and then doing negative b, there's the vector a minus b, which you could have gotten if you had started at the head of b and drawn the vector that goes to the head of a. That is the same vector a minus b.
If it wasn't at the origin,
Say that one more time.
if it wasn't like at the origin, or is it always at the origin? Like this
Well,
way?
so the thing is, you can draw the vectors wherever you want. We just usually like to start at the origin because it makes it easier to see what's happening.
So could we just draw at the origin?
Yes, yeah. Calculating a minus b, that's just going to be the vector 3i plus j minus I plus 5j, which is going to be 3i minus I, which is 2i, and j minus 5j, which is minus 4j. And that certainly looks like what we're doing. If we start here, it looks like we're going over 2 and down 4. Or if we start here, it looks like we're going over 2 and down 4. So adding vectors, subtracting vectors really couldn't be more straightforward. We're just adding the components or subtracting the components. And then we can kind of look at an example problem. So let's say we have this example here. A plane is flying east at 100 miles per hour. By the way, I've just given you a vector, right? I have a speed and a direction, or a magnitude and a direction. And the wind is blowing 20 miles per hour towards 60 degrees north of east. What is the resulting speed of the plane? Well, let's draw our vectors. So here's the vector for the plane. It's going east, which is to the right, 100 miles per hour. And then the wind is going at 20 miles per hour and it's going 60 degrees north of east. So instead of going straight to the east, I'm going to make a 60-degree angle towards the north with that eastward bound. So I'm going this way, 20 miles per hour. And that angle right there is 60 degrees. Now the question is, what's the resulting speed of the plane? I.e., what's the resulting magnitude of this vector that you get when you add these two vectors together? Okay. So to easily add these vectors together, I really need to kind of write them in their component forms. So the vector for the plane is fully to the right. So it's going to be 100i plus 0j. There is no y component, it's all x component. But what about this other vector? The wind going 20 miles per hour at a 60-degree angle. That's got some x component and some y component, or some i and some j. So to find out what the i and j components are, I need to use trig function. Bless you. So looking at this, right, I've got this here. I've kind of got, here's my 60-degree angle. Here's my 20 mile per hour wind. I need to find the x component and the y component. Well, good thing I know how to find cosine and sine of 60 degrees. So I can see here that cosine of 60 degrees is going to equal the x component over 20. Cosine of 60 is 1/2. So 20 times 1/2 is going to be the x component. The x component is going to be 10. And then the other one, I'm going to have sine of 60 degrees equal to the y component over 20. Sine of 60 is root 3 over 2. So root 3 over 2, root 3 over 2 times 20 is going to be y. So y is going to be 10 root 3. So the wind here, we can write the wind vector as 10 in the I direction plus 10 root 3 in the j direction.
Wait, what's in this third?
Sorry, I know, yeah, that's a fair question. Sine of 60 is square root of 3 over 2. And yeah, I know that looks really terrible. So that becomes root 3 over 2 equal to y over 20. And then we get y equal to 20 times root 3 over 2, which is 10 root 3. Other questions? Okay, so now if I want to find this resulting vector's length, I'm going to add these two vectors together and then find the magnitude of that vector. This vector up here is the wind vector plus the plane vector. And adding those vectors together, I get 10i plus 10 root 3j plus 100i plus 0j. In other words, I get 110i plus 10 root 3j. And then to find the magnitude of that vector, the magnitude of the vector w plus p is going to be, magnitude of a vector is always just the square root of the squares of each component added together. Just like it's, okay, or in other words, it's the distance formula, where your end point is 110 to the right, 10 root 3 up, and your beginning point is 0, 0. So there's 0, 0. There's the point 110 comma 10 root 3. And you're just finding the distance between those 2 points. And that's going to be the square root of 110 minus 0 squared plus 10 root 3 minus 0 squared. But really the magnitude of a vector is just take each component, square it, add it together, take the square root. And then simplifying this, 110 squared, something, you get 11 squared is 121, so it's going to be 12,100 plus 10 root 3 squared is 100 times 3, which is 300. So you get the square root of 12,400, which is approximately 111.3 miles per hour. So that is the resulting magnitude of the vector. That's the resulting speed of the plane. Plane flies 100 miles an hour to the east, and the wind blows at 20 miles per hour, 60 degrees north of east. The plane will end up flying an actual speed of 111.3 miles per hour. Kind of neat. Okay. But it's all well and good adding vectors, but we really more care about how we multiply vectors together. Multiplying vectors together is a whole other thing, which you'll definitely see a lot of when you take 22A. A lot of multiplying vectors together in 22A for sure. So how do we multiply two vectors? Well, there are two answers to that question. One way is using what's called the dot product, also known as the scalar product, so called because the result produces a scalar or a real number. The other way is what's called the cross product, also known as the vector product, because the result is a vector. So I really want to emphasize here, when you dot two vectors together, you don't get a vector back. You get a real number back. When you cross two vectors together, you get a vector back. Okay, so let's talk about the dot product first. The dot product of vectors u and v is defined to be the following. U dot v. I do encourage you to, when you do a dot product, to make that dot look a little bit more dotty than like your multiplication. I know it's the dumbest, but make it kind of a slightly bigger dot than if you're just multiplying things together. Or just make sure you write arrows on top of your vector so that someone knows you're dotting vectors together. The dot product of two vectors is equal to the magnitude of each vector multiplied together times the cosine of the angle between those two vectors. So if your vectors look like this, here's u, here's v, and here's the angle between them, you would calculate the dot product between them, or you could calculate the dot product between them as magnitude of u times magnitude of v times cosine of the angle between them.
Wait, what are those?
So these just means, so this symbol here, that just means the magnitude of whatever. So this is the magnitude or length of whatever vectors inside there. So if that's like your vector v, then this is the magnitude or length of the vector v. And I will again, I'll reemphasize here. Sometimes people just use a single like absolute value looking thing. So you can write it like this, but I will just really mention here. Sometimes people write it as just like an absolute value of your vector. Literally means the same thing, it's just less writing. So people often default to this because it's kind of easier to write. But if you see a vector inside absolute values or double absolute values, you know, oh, they're just asking for the magnitude, aka the length of that vector. We'll do one example like this, but I will tell you, usually you're not going to know the angle between two vectors. It's not something that's usually given information. But here's an example that's not too terrible to calculate. Let's say we have, those are boring, that's fine. Okay, fine, we can do that. Let's say we have u equal to 2i and v equal to 3j. So here's u and here's v. The angle between them is clearly 90 degrees because one of them is purely horizontal, one of them is purely vertical. So I want to find u dotted with v. It's going to be the magnitude of u. Also, nice thing about a vector that only has one component, its magnitude is the absolute value of that number. So the magnitude of u is just 2 because the length of u is 2. And the magnitude of v is 3. And the angle between them is 90 degrees. So what we're getting here is 2 times 3 times cosine of 90 degrees is 0. Fun fact, whenever vectors are perpendicular, their dot product is 0. In fact, that's an if and only if statement. Vectors are perpendicular if and only if their dot product is 0. So u is perpendicular to v if and only if, that's what the double F means, u dot v is equal to 0. Let's look at one more example though, because I want to show you an example that we can kind of see how the actual way we're going to calculate them works. So let's say I have vectors. Sure. I'm trying to think of an example that's not too terrible. Yeah, let's say we have that u is equal to the vector. Yeah, we'll do that one, sure. 2i plus 2 root 3j. And v is equal to the vector. Sure, let's go that way. Just 4j. I'm going to draw them. So 4j is easy enough to draw. There's u. And sorry, there's v, apologies. There's v. And u, I'm going over 2 and up to root 3, which is about, root 3 is about 1.75, so 1.73 really, so about 3.5. But notably, that's kind of a 30, 90, 60, 30, 60, 90 triangle kind of values, right? If you go over 2 and up to root 3, well, that angle there is wrong. Did I blow it? No, that seems right. Yeah, sorry. Yeah. That angle is going to be 60 degrees. Because we can see here that, well, if we find the length of u, which we're going to find anyway, the magnitude of u is the square root of 2 squared plus 2 root 3 squared. which is the square root of 4 plus 4 times 3 is 12, which is the square root of 16, which is 4. This triangle has a cosine value of 1/2, 2 over 4, and a sine value of root 3 over 2. And the angle that goes with those values is 60 degrees. The reason I point that out is because now we know the angle between U and V is actually 30 degrees. So we could totally calculate U dot V as the magnitude of U times the magnitude of V times cosine of the angle between them, which is 30 degrees, which ends up being, well, the magnitude of U we just calculated was 4. The magnitude of V is obviously 4 because it's just straight 4 up. And cosine of 30 degrees, well, cosine of 60 degrees is 2 over 4, which is 1/2. Cosine of 30 degrees is the other value that goes with that, which is root 3 over 2. And we end up getting 16 divided by 2 is 8 root 3. Okay, but usually you're not going to go know the angle between two vectors. And so here's the thing. We can calculate the dot product in a much, much, much simpler way. U dot V, which is the vector 2i plus, sorry, I wrote it in this weird way. Apologies, 2i plus 2 root 3j dotted with 0i plus 4j. You can find the dot product of two vectors by multiplying the corresponding components together and adding up the results. So this is going to equal 2 times 0 plus 2 root 3 times 4, which ends up being 0 plus 8 root 3, which is 8 root 3. Same value. And that is the thing that we really want to know, is that when you want to find the dot product of two vectors, you don't need to know the angle between them. What you need to know is just how they're written component-wise, and then multiply their components together, add the results, you're done. That is how you find the dot product of two vectors. So for example, if I want to find, say, if U is equal to 2i plus 3j, and V is equal to 3i plus 4j, I can very easily find the dot product of U and V. U dot V is going to be 2 times 3 plus 3 times 4, which is 6 plus 12, which is 18. Cool. What is the dot product exactly? Good question. I don't know exactly how to say it well, but what I've kind of seen over the years is it's essentially the amount of how do I say it right? It's the amount of each vector that's in the other vector's direction multiplied together. So back in this example, how much of U is in the direction of V? 0. And how much of V is in the direction of U? Also 0. And if you multiply those together, you get 0. Whereas here, it's a little bit of a weirder question. How much of U is in the direction of V? Well, 2 root 3 of it. And how much of V is in the direction of U? Well, about 4 of it. And 4 times 2 root 3 ends up being 8 root 3. It actually is a true statement, what I'm saying. It's just not a very, it's not a good physical interpretation. Like, you're like, oh, the dot product means you take how much of this is this and this is that and multiply them together. Yeah. But it is actually true. And one more thing to say about the dot product here is if you have vectors in the same direction, like say U equal to 5i and V equal to 3i, then their dot product is just going to be the product of those two things. So U dot V is going to be 5 times 3, which is 15. Which again, still corresponds to what we were saying. They're both exactly in the same direction, right? Here's U being 5i, and here's V being 3i. And the amount of U that's in the direction of V is 5. And the amount of V that's in the direction of U is 3, and 5 times 3 is 15. Okay. What I think is interesting about this is we can use the dot product to then find the angle between two vectors. And that's kind of a more typical thing. So we can say, for example, I want to find the angle between, let's say, U equal to 2i plus j minus 2k, and V equal to 3i plus 4k. here's the idea. We have that the dot product of two vectors, we can calculate it in the usual nice multiplying components together way. But we can also calculate it or think of calculating it in the magnitude of u times magnitude of v times cosine of the angle between them sort of way. Well, we can take this equation and solve for theta. We divide both sides by the magnitudes. U dot v divided by the magnitude of u times the magnitude of v is equal to cosine of theta. And then if I take the inverse cosine of both sides, inverse cosine of u dot v over the magnitude of u times the magnitude of v is equal to the angle theta. I will point out, and I would not be surprised at all if Casals mentions this. This kind of relates to or relies on what's called the Cauchy-Schwarz inequality, which is the fact that this fraction has to be less than or equal to 1 and bigger than or equal to -1, because you can't take the inverse cosine of a number bigger than 1. There is no value, right? Inverse cosine of 2 doesn't exist. There's no angle where cosine is equal to 2. So it's really, really true here that u dot v divided by the magnitude of u times the magnitude of v plus u is less than or equal to 1 and is bigger than or equal to -1. Or put more simply, the absolute value of u dot v is less than or equal to the magnitude of u times the magnitude of v. And that is the, I believe, I'm pretty sure, now that I say it, I'm pretty sure that's the Cauchy-Schwarz inequality, which comes up a lot in higher mathematical classes. But,
You're saying on the left side, it's a magnitude, so an absolute value.
so what I did was I said, so what I really did, I skipped a step. I said, I'm going to multiply, instead of saying u dot v over magnitude of u magnitude of v is between -1 and 1, I'm just saying the absolute value of it is less than or equal to 1. And then I'm bringing the magnitude of u and magnitude of v up into the other side over here. We can still use this to find the angle between these two vectors. So usually when I find the angle between two vectors, I like to start with finding cosine of the angle. I don't know why, it just feels like a more natural progression. So if I was doing this problem, I would say, okay, great. Cosine of the angle between these two vectors is going to be u dot v, so 2i plus j minus 2k, dotted with 3i plus 4k over the magnitude of each of those vectors. So the magnitude of 2i plus j minus 2k times the magnitude of 3i plus 4k. And then we dot the vectors together. So let's see, 2 times 3 is 6. 1 times 0, right? There isn't a j component over there. So I just get a 0 from that part. And then -2 times 4 is -8. Divided by the magnitude of 2i plus j minus 2k is the square root of 2 squared plus 1 squared plus -2 squared. And the magnitude of 3i plus 4k is 3 squared plus the square root of 3 squared plus 4 squared. So I end up with 6 minus 8, so -2 over 4 plus 1 plus 4 is the square root of 9, and 9 plus 16 is the square root of 25. This actually comes out to be relatively nice. I get -2 over 3 times 5. -2 over 15. And that's equal to cosine of theta. All right. Knowing that cosine is negative means my angle is going to be in the second quadrant, because cosine can't be negative in the first quadrant. So then I'm going to say that my angle is just equal to the inverse cosine of -2 over 15, which is approximately, let's see, inverse cosine, -2 over 15. Getting 1.7, which means what? It means my calculator is probably in radians, right? Because 1.7 degrees is not in the second quadrant. So I mean, you could write your answer in radians, although it feels, even though we like to say calculus works better in radians, a lot of the times we still like to write our answers in degrees because it's just more palatable. So I would probably switch this up and multiply that by 180 over pi, and get about 97.66 degrees. Just be aware when you're answering questions, if you need to be answering them in radians or degrees. I believe that WebWork defaults to radians. So if you're answering angle questions in WebWork, start with radians unless they specifically say degrees. That's my piece of advice. Let's look at one more example of this because there's kind of a cool example I like to show. So let's find the bond angle between the carbon and one of the hydrogen atoms. I feel like it's really two of the hydrogen atoms, but whatever. On a methane molecule. And not that I'm good at chemistry, but I know that a methane molecule is CH4. And the shape is a tetrahedron. Tetrahedron with the carbon in the middle. Here's how this kind of looks. So plotting this in the three-dimensional coordinate system. So tetrahedron, you can think of as kind of like the opposite ends of a cube on top and the opposite ends of a cube on the bottom. Let me show you what I mean. So here's a cube. Can I draw a cube? Maybe. Probably. Great, there's a cube. And we could put the hydrogen atoms here and here and there and there. And that gives, if you connected those up, it does in fact give you a tetrahedron. You can kind of see. But you've got four triangular faces, right? The one there, the one there, the one there, the one there. And then we're going to put the carbon in the middle. So let's give these things some names. Let's say this is the point 0, 1, 1. This is the point 1, 1, 0. Here's the point 1, 0, 1. And here's the origin, which I don't think I need to label. And then the carbon being in the middle of this cube means it's got a coordinate of 1/2, 1/2, 1/2. So if I can draw that somewhat well, let's go 1/2 this way, half that way, half that way. So maybe right about there. Here's your carbon at the point 1/2, 1/2, 1/2. What we're going to do to find the angle that that carbon makes with the two hydrogen bonds, say like there and there, is we're going to find the vectors that emanate from there that go to there. So we have two vectors. Let's call this one U and this one V. U is the vector that starts at the point 1/2, 1/2, 1/2. And ends at the point 0, 0, 0. We haven't really talked about this, but if you want to find the vector that starts at one point and ends at another point, you take your end point and you subtract off the beginning point. That means U is going to be the vector -1/2, -1/2, -1/2. Or if you prefer, -1/2 I minus 1/2 J minus 1/2 K. And then V is going to be the vector that ends at 1, 1, 0 and begins at 1/2, 1/2, 1/2. So V is going to be the vector 1 minus 1/2 is 1/2, 1 minus 1/2 is 1/2, and 0 minus 1/2 is -1/2. Or if you prefer, 1/2 I plus 1/2 J minus 1/2 K. And now we totally have all the information we need to find the angle between these two vectors. So the angle, well, I know that cosine of the angle is going to be U dot V over the magnitude of u times the magnitude of v. I think you can do as much or as little writing here as you want to do. I don't really want to write out all of u and all of v and then dot them together. I'm just going to find what it is. So if I do u dot v, well, u dot v is going to be negative 1/2 times 1/2, which is negative 1/4. And negative 1/2 times 1/2, which is another negative 1/4. And negative 1/2 times negative 1/2, which is a positive 1/4. The magnitude of both these vectors is actually going to be the same. The magnitude of u is going to be the square root of 1/2 squared plus 1/2 squared plus 1/2 squared, which is the square root of 1/4 plus 1/4 plus 1/4, which is 3/4. And the magnitude of v is also going to be the square root of 3/4. So simplifying this a little bit, we end up with a positive 1/4 on top and a negative 1/4 on top, apologies, and a positive 3/4 on the bottom, or a negative 1/3 overall. So theta is going to be equal to the inverse cosine of negative 1/3, which is approximately 109.5 degrees. Which is kind of interesting to know that, I mean, actually, like, this is a real molecule in the world, and this is actually the angle between the carbon in the middle and two of the hydrogen bonds adjacent to it. It's not nothing. It's interesting. Okay. Sorry. One thing we often do with dot products is we use them to find how one vector is projected onto another vector. And we got enough time to say this last. We'll say this last thing, and that'll be okay. So, let's say we have these two vectors. So here's our vector v, and here's our vector u, and here's the angle between u and v. And if I literally just drop a perpendicular down onto v from u, this vector here, starting at the same place you started and v started, and there, that vector there is the projection of u onto v. And we often say that the component of u onto v is just the magnitude or length of that projection. But it's something we kind of talk about frequently, so we give it a name. Okay, so to find the projection of u onto v, we're first going to find the magnitude of the projection, often called the component. So using some trigonometry, let's see. Well, I can see that cosine of the angle there is equal to that length, which we're calling the component, divided by the magnitude of u. And here's a trick that you're probably going to employ a lot in the next couple weeks. If you see cosine, you should think, all right, I need to make the dot product appear somehow. On the other hand, if you see sine, we're going to talk about trying to make the cross product appear, because cosine goes with the dot product and sine goes with the cross product. So what I'm going to do is I'm going to multiply both sides by the magnitude of u and the magnitude of v. So I want the magnitude of u times the magnitude of v to show up over here. So I'm going to do magnitude of u times magnitude of v times cosine theta equal to the component over there of u onto v divided by the magnitude of u times the magnitude of u times the magnitude of v. I don't know who chose u and v. Bad choice, because they look kind of the same. These cancel. This is equal to u dot v, because it's the magnitude of u times the magnitude of v times cosine of the angle between them. So you have u dot v equal to the component of u onto v times the magnitude of v. And dividing by that, we end up with the component of u onto v is equal to u dot v divided by the magnitude of v. That's why we do it that way, because it works out relatively nicely. And then to find the actual vector, well, here's where we're going to use the idea. A vector is a length times a direction. So this projection, the length or the magnitude, is equal to the component of u onto v, which is just u dot v over the magnitude of v. What direction is this vector pointing in? or, right, the direction of V. So the direction here is just going to be the direction of V, which is V divided by its own magnitude. Right, you have, when you're finding a direction, you have to have a unit vector. So you have to take whatever vector you've got and divide it by its own length so that the new length is a length of 1. So then finally, we can say that the projection of U onto V is equal to these two things multiplied together. So it's U dot V over the magnitude of V times the vector V, not dotted, these parentheses, times the vector V over the magnitude of V. Or as is often written, U dot V over the magnitude of V squared all times the vector V. Or as it is often written, here's a fun fact. I say fun fact too much, but anyways, it is a fun fact. The magnitude of V squared is just the vector V dotted with itself. Just to kind of end on that note, if V is equal to the vector A times I plus B times J plus C times K, well, V dotted with itself is just A times A plus B times B plus C times C. But the magnitude of V is just the square root of A squared plus B squared plus C squared. So of course, the magnitude of V squared is the same thing as V dot V. It's a pretty common back and forth people use all the time. So your professor might just go straight from saying, oh yeah, magnitude of V squared is V dot V, no especially explanation needed because it's relatively straightforward.